Welcome to this explainer. There's a problem that plagues almost every programmer at some point: managing scattered, disjointed data. Have you ever found yourself juggling 5 completely different variables just to keep track of one single entity in your code? Well, today, we're going to fix that by exploring the incredibly elegant architecture of C++ structs. We'll be taking a builder's journey, transforming chaotic data into beautifully structured digital skyscraper.
So here's our blueprint for today. 1. What are C++ structs? 2. Accessing members with the dot operator. 3. Struct operations and functions. 4. Combining arrays and structs. And 5. Structs within a struct. Let's get right into it.
Section 1. What are C++ structs? Let's check out the blueprint. Let's start with the fundamental blueprint of data organization to understand what a struct actually is in the C++ landscape. To really grasp this, think of a struct as a digital manila folder. It's a single definition that acts as a unified record, securely holding a fixed collection of totally different document types. In the older days of programming, if you wanted to track a student's name, their ID, and their GPA, you'd have to create 3 completely separate variables and just kind of hope they stayed synchronized. A struct solves this by bundling them all into one cohesive unit. You define the folder once, and then you can create as many copies of that folder as you need.
Okay, let's dive into the syntax. Notice the raw skeleton definition here that outlines the members. You start with the keyword struct, followed by whatever name you want to give it. Inside those curly braces, you group the data types and their identifiers. But listen, here is a massive pitfall that so many beginners fall into. Crucially, this definition absolutely has to end with a semicolon. If you forget that semicolon after the closing brace, your compiler is going to throw errors that seem to make no sense at all. And remember, at this stage, this is literally just a blueprint. No actual memory has been allocated yet.
And this brilliantly illustrates the concept in action. By looking at this concrete student type example, we can see how completely different types, like strings for names, characters for a course grade, integers for test scores, and a double for the GPA, can all live perfectly together under one cohesive record. Right below the definition, you can see the variable declarations. When we type student type new student, that is the exact moment the compiler finally listens to our blueprint and physically allocates the memory for that specific manila folder.
All right, moving on to Section 2, accessing members using the dot operator, the skeleton.
Now that we've got our digital folder safely stored in memory, we need to know exactly how to open it and interact with the specific papers inside. We use the dot operator. Think of it as the physical key you use to unlock and access the individual members of our struct variable. Without it, the struct is just a sealed box. But with it, you have absolute control over every single piece of data inside.
The syntax rule here is incredibly straightforward. To read or change a value, you just type the struct variable name, add a dot, and then specify the exact member name you want to access. It honestly reads like plain English. Hey, go to this specific struct and give me this specific member.
Watch how we use this syntax in practice. We start with our newly declared new student variable. It's an empty skeleton right now. The memory's there, sure, but it's totally filled with garbage data. But when we apply our dot operator, doing things like setting newStudent.firstName to John and newStudent.GPA to 0.0, we transform that empty skeleton into a fully initialized student record. It is precise, it's clean, and it's incredibly easy to read.
Section 3. Struct operations and functions, the physics.
Next up, let's explore the laws of physics governing structs. By that, I mean what operations C++ actually allows us to perform on them as whole units. What's really fascinating is the strict boundary C++ places on structs. While you can conveniently copy an entire struct using a simple assignment statement, like student equals new student, you are strictly forbidden from performing aggregate relational comparisons or aggregate input and output. What does that actually mean for you? It means you literally cannot say if student equals new student. The compiler has no idea how to compare these custom folders. You also can't just count the student. For comparisons and I/O, those actions must be handled member by member using that dot operator we just learned.
So a really crucial point here is understanding how structs compare to other data structures. Notice the sharp contrast to aid your memory. Unlike arrays, which don't even let you do aggregate assignment, structs do allow aggregate assignment, and they can even be returned as a value directly from a function. Arrays simply cannot do that in standard C++.
And speaking of functions, this snippet proves how elegantly a massive struct can be passed as a single parameter to keep your input and output code beautifully organized. Just look at that print student function. Instead of passing 5 or 6 separate variables into the function parameters, we pass one single student type variable. The function then uses the dot operator to cleanly output every single member. You can pass these by value, like we're doing here, or by reference if you actually need to modify the original struct inside the function.
Section 4. Combining arrays and structs. The multiplier.
Let's see how this builds our capabilities even further by combining structs with another foundational C++ concept, arrays. Before we look at the code, it is absolutely crucial for your mental model to distinguish between two distinct concepts: nesting an array inside a single struct versus creating a large array list composed of multiple struct items. These sound super similar, but they serve entirely different architectural purposes.
First, let's look at an array in a struct. We have a list-type struct here. Notice that an array named listelem is acting as a component living right inside the struct, bundled perfectly together with an integer called list_length. Now, why do this? Well, because in standard C++, arrays don't actually know their own length. By wrapping the array and a length variable together inside a single struct, you create a completely self-contained list entity. Whenever you pass this struct to a function, the array and its current length travel together. It's a massive quality of life upgrade.
Pivoting to the other side, this model illustrates an array of structs. Instead of having one folder with an array inside it, I want you to imagine a massive filing cabinet drawer. This essentially multiplies our single building block to create a robust database. You can declare an array of up to 50 distinct employee-type records. So, to access the first name of the third employee, you'd go to the filing cabinet first, employees bracket 2, and then use your key, .firstname. It's an incredibly powerful way to scale up your data.
Section 5. Structs within a struct. The skyscraper.
For the climax of our explainer, let's explore how to build true digital skyscrapers by nesting these components into one another. Just look at the raw complexity of this massive employee structure. It has over 20 different members totally crammed together. We've got first name, middle name, last name, address 1, address 2, city, state, zip, and then we have hire month, hire day, hire year, quit month, quit day, quit year. It's completely overwhelming. It makes it incredibly unwieldy for a programmer to manage, and honestly, it's just full of repetitive concepts.
When you're looking at an overwhelming list like that, you really have to pause and ask yourself a vital software engineering question. How can we make this code cleaner, more modular, and more logical?
The answer? Nesting structs. By creating specialized, completely separate records for common concepts like a name type, an address type, a date type, and a contact type, we can actually reuse them. Notice how we use the date type struct twice inside the employee struct, once for the hire date and once for the quit date. By placing these specialized building blocks inside the main employee struct, our data model goes from a sprawling mess to an incredibly elegant, readable architecture. And to access a nested member, you just chain the dot operators together. For example, employee.hiredate.year. It's logical, it reads perfectly, and it is highly modular.
We've covered some really incredible ground today. We took scattered, loose variables and bound them into unified records. We unlocked them with the dot operator, learned the rigid laws of struct physics, integrated them seamlessly with arrays, and finally constructed towering, nested structures. So now that you've mastered this builder's journey from simple records to nested digital skyscrapers, I leave you with this. How will you architect your next great program? Happy coding and keep building.